Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, India. Today we are going to discuss about the module SEM instrumentation, which is the second part of the scanning electron microscope we studied last time from the paper Characterization of Materials 2. So students, let us see what we are going to learn this model. First, we will learn about the fundamentals of scanning electron microscopy. Then we will see about the SEM instrumentation, and finally we will study the SEM imaging modes. All the electron beam instruments are built around an electron column which produces a stable electron beam that controls the beam content, beam size and beam shape and rasters the beam. Electron optics are a very close analog to light optics, and most of the principles of an electron beam column can be understood by thinking of the electrons as rays of light and the electron optical components as simply their optical counterparts. A scanning electron microscope is an electron microscope that utilizes the focused beam of electrons to produce images of a sample surface. Various signals are produced by electrons' interaction with atoms of the sample that contain information about the sample's surface topography and composition. The electron beam is scanned in a raster pattern, and the beam's position is combined with the detected signal to produce an image. Specimens can be imaged in high vacuum, in low vacuum, in wet conditions, and at a wide range of cryogenics or elevated temperatures with resolution better than 1 nanometer. SEM instrumentation. The major components of SEM are sources, electron column and sample chamber. A schematic diagram of SEM instrumentation is shown in figure 1 with a brief description of each system will be followed in this session. The source. Electrons are produced at the source by thermionic heating. These electrons are then accelerated to a voltage between 1 to 40 kilovolt and condensed into a narrow beam which is used for imaging and analysis. Electron gun. It is located at the top of the column where free electrons are generated by thermionic emission from a tungsten filament at near about 2700 K. The filament inside the wellnet controls the number of electrons leaving the gun. Electrons are primarily accelerated towards anode, adjustable from 200 volt to 30 kilovolt. Figure 2 schematizes the components used for developing the electron gun that includes filament, wellnet cylinder and anode. Emission of the beam is of two types: thermal emission and field emission. Thermal emission uses heat to excite the electrons from the filament. The filament current can be controlled by the control knob for heating of the filament. Increasing the filament current increases the temperature, leading to increase the number of electrons emitted by the filament and saturates at a certain point, beyond which an increase in filament current will have no effect in the emitted electrons. Continuous increment in filament current further raises the filament temperature and hastening filament could burn. This is called the saturation point. Exceeding the required filament temperature for the saturation point will decrease the life of the filament significantly. Adjusting the filament current below the saturation point results in unstable beam current and a poor image. There are three types of thermal emission filaments: tungsten filaments, LaB6 filament that are a single lanthanum hexaboride crystal, and cerium hexaboride, generally abbreviated as CeB6 filaments, are similar to LaB6 filaments. Tungsten filament in hairpin shape, consisting of an inverted V-shaped wire of tungsten about 100 micrometer long, and is heated resistively to produce electrons. This is the most basic type of electron source. Lanthanum hexaboride or cerium hexaboride, these are thermionic emission guns. It is the most common high brightness source. This solid state crystal source offers about 5 to 10 times the brightness and a much longer lifetime than tungsten. Field emission does not make use of heat to excite the electrons from the filament. Field emission guns are cold electron source because these electrons are not released from the heated filament as in the conventional thermal emission gun, and the electrons are pulled magnetically. The filament consists of fine pointed tungsten wire, ideally one atom across the tip, that is kept at a high negative charge along with the rest of the cathode, while keeping at a positive charge. The large difference in potential on a small point pulls the electrons of the filament. Advantages and disadvantages of the field emission. The advantages in the system with field emission includes: the emission is cool, the emitted beam is much smaller in diameter, which is called a better resolution, and filament life is generally longer. This disadvantage includes much higher vacuum is required, approximately 10 to the minus 7 torr, and special pumps without oil diffusion is needed for operation. Any debris sticking on the fine tip of the filament will cause a reduction in emission. Thus, the microscope needs to be baked out routinely to maintain a clean electron gun. Another disadvantage of field emission is long acquisition times during X-ray analysis. Field emission gun will not generate many X-rays since low beam currents and the small beam diameters are generally used. Electron column, it consists of apertures, condenser lenses, and vacuum system. The function of these apertures is to reduce and exclude extraneous electrons in the lenses. One or more apertures may be found in the electron column depending on the microscope. The final lens aperture located below the scanning coils that determine the diameter or spot size of the beam at the specimen and helps determining resolution of the image. Decreasing the spot size allows increase in resolution and depth of field. The condenser lens. After the beam passes through the aperture of the anode, it is influenced by two condenser lenses which are electromagnetic in nature, converging the beam to pass through a focal point and focus down to 1000 times its original size. In conjunction with the selected accelerating voltage, the condenser lens primarily responsible for determining the intensity of the electron beam when it strikes the specimen. The vacuum system. The ability for the SEM to provide a controlled electron beam requires the electron column to be under vacuum at a pressure of at least 5 into 10 to the minus 5 torr. A basic requirement for the general operation of the SEM is to control and operate the vacuum system required for a variety of reasons, including the first one, the current that passes through the filament causes the filament to reach temperatures around 2700 degree K. A hot tungsten filament will oxidize and burn out in the presence of air at atmospheric pressure if the chamber will not be evacuated by removing oxygen and water contents. Second, the ability of the column optics to operate properly requires a fairly clean, dust-free environment. The third, air particles and dust inside the column can interfere and block the electrons before it reaches the specimen in the sample chamber. To pump out from the atmospheric pressure down to 10 to the power minus 6 torr, two classes of pumps are used. A low vacuum pump at an atmosphere down to 10 to the minus 3 torr and a high vacuum pump that can go to 10 to the minus 3 down to 10 to the minus 6 or greater depending on the type of the pump. Separate pumps in conjunction can provide good vacuum pressure relatively quickly and efficiently, and the connections are as shown in figure 3. A majority of the initial pumping is done by the action of a mechanical pump, often called a roughing pump. The roughing pump operates first during the pump down process and has excellent efficiency above 10 to the minus 2 torr. Pressures below minus 2 torr are acquired by the action of a turbomolecular pump operated by a turbine that rotates at 20,000 to 50,000 rotations per minute to evacuate gas molecules and particulates found inside the column. A valving system is used to change over between the two pumping systems whenever a change in vacuum is required. Electron beam manipulation. The electron beam from source is focused by applying electrostatic and magnetic fields before it falls on the interface of the specimen. In the electron gun, electrons are controlled by an electrostatic field, while throughout the rest of the SEM, the electrons are controlled by magnetic lenses. Electrostatic lenses are formed when negative and positive fields are near each other. This is the situation between the gun and the anode. Magnetic fields are used to form electron microscope lenses. These lenses are known as electromagnetic lenses. Most ACMs use several electromagnetic lenses to reduce the size of the beam's crossover spot, is known by condensed lenses. Electromagnetic lenses have spherical aberration, which is the inability of the lenses to image central and peripheral portions of the electron beam at the same focal point. This is plotted in figure 4a. As the barrier passes through the final condenser lenses, two sets of magnetic scanning coils move the beam. These readily opposing magnetic coils and allow scanning in both the x and y direction, and the schematics is given in figure 4b. The scan pattern is called a raster pattern, and the coil are known as raster coils. The raster pattern covers the specimen by starting in the upper left corner and proceeding to the right, then dropping down one line with each line scanned. It is these coils that give the scanning electron microscope its name. The specimen chamber. The specimen stage and controls are located at the lower portion of the column. The secondary electrons from the specimen are attracted to the detector by a positive charge in the specimen chamber. Signal detection begins when primary electrons of the electron beam enters the specimen and travels some distance into the specimen before hitting to another particle, and results the formation of a teardrop shaped reaction vessel as shown in figure 5. The reaction vessel by definition is where all the scattering events are taking place. Small reaction vessels tend to give better resolution, while larger reaction vessels tend to give more signal. The volume of a reaction vessel depends upon the atomic density, topography of the specimen, and the acceleration potential of the primary electron beam. Different events occur in the reaction vessel includes backscattered electrons, secondary electrons, X-rays, cathodoluminescence, and transmitted electrons. First, the backscattered electrons. A primary electron beam may be scattered in such a way that it escapes back from the specimen without transmitting through the specimen. Backscattered electrons are identical to the originally incident electrons. Operating in the backscattered image mode is useful when relative atomic density information in conjunction with topographical information is to be displayed. Second, the secondary electrons. Secondary electrons are generated when a primary electron dislodges a specimen electron from the specimen surface, or can also be generated by other secondary electrons. These electrons have a low energy of only a few electron volts, thus can only be detected when they are dislodged near the surface of the reaction vessel. Therefore, secondary electrons cannot escape from deep within the reaction vessel. Secondary electrons that are generated but do not escape from the sample are observed by the sample. Two of the foremost reasons for operating in the secondary electron imaging mode are: first, to obtain topographical information and high resolution, and the contrast and soft shadows of the image closely resemble that of a specimen illuminated with light. Thus, image interpretation is easier because the images appear more familiar. Second, the primary beam electrons may give rise to several secondary electrons by multiple scattering events, potentially increasing the signal. With an increased signal and shallow escape depth of secondary electrons, the spatial resolution in the secondary mode can be greater than in the other modes. Atomic density information also can be obtained because some materials are better secondary emitters than others. The use of secondary electrons to determine atomic number is not as reliable as with the backscatter mode. Now, the third event occurs in the reaction vessel or X-rays. The X-rays are emitted when electrons are dislodged from specific orbits of an atom in the specimen. Elemental information can be obtained in the X-ray mode. X-ray spectrometer detectors measure wavelength or energy level. These are two types of detectors used in X-ray analysis. The fourth one is cathodoluminescence. Some specimen molecules show fluorescence when exposed to an electron beam. In the SEM, this reaction is called cathodoluminescence. The fluorescence produces light photons that can be detected, and few SEMs are equipped with capability of detecting these photons. The fifth event occurs in the reaction vessel is transmitted electrons. If the specimen is thin enough, the primary electrons may pass through the specimen. These electrons are known as transmitted electrons and can provide atomic density information. The atomic density information is displayed as a shadow. The higher the atomic number, the darker the shadow until no electron pass through the specimen. Detectors collect this signal generated from interaction of beam with specimen. Electronics of the detectors convert the signal into digital images as shown in figure 6. An electron detector magnetically attracts the emitted secondary electrons by a 200 volt potential applied to a ring around the detector. Upon entering the ring, the electrons are attracted and accelerated by the 10 kilovolt potential onto the scintillator. The electrons hit the scintillator, causing photons to be emitted. Photons emitted from the scintillator travel down the light pipe hitting the photomultiplier tube. The function of the photomultiplier tube is to increase or amplify original signal. Thus, for every photon generated, several electrons will be produced, resulting a significant amplification of the original signal. The amount of amplification of the photomultiplier tube is controlled by the photomultiplier voltage control. SEM imaging modes. The imaging modes in SEM are controlled by 4 different parameters and is sketched in figure 7. The diameter size of the electron probe dP, the diameter of electron beam focused at the specimen, the electron probe current, which is the current impinging upon the specimen when generating various signals, the The third parameter is the convergence angle of electron probe, which is half cone angle of electrons converging onto the specimen that controls the imaging. Fourth is the accelerating voltage for the electron beam. Resolution mode. This mode is governed by the diameter of the electron probe, dp. Resolution refers to the size of finest detail that can be captured. To image the finest details, dp must be comparable with or smaller than the features itself. The mode becomes meaningful only at high image magnification, which is more than 10,000x. The high current mode. This mode is governed by the electron probe current IP. Large IP is recommended for the best image visibility and quality as it helps overcoming random noise. The beam current is basically restricted by the spot size and will thereby cause brightness and contrast compensations. Smaller spot size requires high brightness and contrast levels. Smaller spot size allows high resolution and a greater depth of field. Figure 8 below shows the effect of spot size on image quality. Depth of focus mode. This mode is governed by the convergence angle of the probe, alpha p. Alpha p should be smaller for the best imaging of the specimen, as the beam diameter changes only a small amount over a long vertical distance and allows the surface features at different heights to appear in focus simultaneously. Low voltage mode. This mode is governed by the acceleration voltage of the beam. At low accelerating voltage less than 5 kV, the beam interaction with the specimen is confined to the regions very close to the surface. This provides an image rich in surface details compared to the images taken at a higher accelerating voltages. The high conductive materials will be better under higher voltages. Higher voltages around 1530 kV generally allow for high resolution at high magnifications, although this can damage the specimen very quickly if it is not highly conductive. The figure below provides the detail of the effects of using high and low accelerating voltages. Emission (ACM). Field emission is an alternate method where potential barrier for electrons is lowered and narrowed by applying a negative potential at a very sharp Y tip of radius less than 10 nanometer cathode. When the tip concentrated field reaches about 10 volt per nanometer, then electrons emit. The epi sources provide enhanced performance, reliability and lifetime. Two classes of field emitters. First is cold field emitter, abbreviated as CFE, and second Schottky field emitters, abbreviated as SFE. The third emitter is thermal field emitters, abbreviated as TFE. The CFE relies purely on the high applied field for electron emission, independent of the tip temperature. TFE has the same property as CFE, but is operated at elevated temperatures. Helps to keep the tip clean, reducing noise and instability even in degraded vacuum conditions. The SFE guns are similar to other FE sources but include a suppressor gate to eliminate the unwanted thermonic emission from region outside the tip. So students, let us summarize what we have learned in this module. The scanning electron microscope is a versatile instrument where an electron probe is scanned across the surface of the sample and detectors interpret the signal as a function of time. A resolution of 1 or 2 nanometer can be obtained when operated in a high resolution setup. Scanning electron microscopy is used for inspecting topographies of specimens at very high magnifications up to 300,000x. During SEM inspection, a beam of electrons is focused on a spot volume of specimen, resulting in the transfer of energy to the spot. These bombarding electrons, also referred to as primary electrons, dislodge electrons from the specimen itself, are known as secondary electrons, are attracted and collected by a positively biased grid or detector. To produce the SEM image, the electron beam is swept across the area being inspected, producing many such signals. These signals are then amplified, analyzed, and translated into images of the topography being inspected. Finally, the image is shown on a CRT. Thank you.